Epoxides are quite useful functional groups. They are readily made from alkenes, and there's two methods that you can make them, either by the per acid method, which is a single-step procedure, or by the two-step procedure of forming a halohydrin and then treating it with base. Let's go over the per acid procedure first. A per acid has a basic structure like so. It's very similar to a carboxylic acid, except you have an oxygen-oxygen bond in there. And the most common per acid that's used is one that's referred to as MCPBA, or metachloroperbenzoic acid. Now this is a nice crystalline compound, but has an unfortunate side reaction of detonating from time to time. And so some people use the per acid that's called MMPP instead. And that per acid looks like so. Where you have two of these and then a magnesium 2+. This is a lot more stable than MCPBA, but either one works. You can use MCPBA, you can write MMPP, or you can just write the basic structure of the per acid, which is probably more useful than any of these two. You can even write RCO3H, where CO3H represents this. So, the way a per acid works, it's a single-step procedure and it's a single-step mechanism. Where the electrons go from the alkene to the oxygen, and lone pair from the oxygen goes to there. Now that creates the three-membered ring. The other arrows are used to remove the bonds to this oxygen. This oxygen-oxygen bond goes between this oxygen and this carbon. And that kicks these electrons up to that hydrogen, and the electrons from the OH bond then go onto the oxygen. It happens all at once, single-step procedure. And you get this epoxide as a product, and as a byproduct of this reaction you get carboxylic acid. So this is the product. Important thing is that it's actually a syn addition, meaning start off with a cis alkene, your epoxide ends up cis. Cis stays cis, trans stays trans. So, bottom case here, mechanisms just the same. The book has a slightly different mechanism that uses less arrows, where the electrons in the alkene go up to this oxygen. these kick these electrons to here, causes these electrons to grab that H, and then these electrons from the OH bond go to that carbon there. So you get 4 arrows instead of the 5 arrows. And that's fine. Either of these two mechanisms is acceptable. Now the epoxide that's made in this case, since we're starting with a transalkene, is a trans epoxide. And since this molecule is chiral, and your starting materials are achiral, this is going to be a racemic mixture of the two epoxides, the two enantiomers. Now the two-step procedure is very similar to it, except happens is you form the bromonium ion first. Electrons go to the bromine, kick this bromide off, lone pair from the bromide goes and adds there. And you get the bromonium ion. Now, since we're dealing with water, so the Br attacking, water attacks. Then water comes, deprotonates, to give the halohydrogen. And this, of course, is racemic. This ends the first step. Second step adds base. And what the base does, it does what all bases do, deprotonates. Deprotonates the oxygen. And then this molecule is set up for an internal SN2 reaction because both this oxygen and this bromide are anti to each other. Since it's an internal SN2 reaction, again, you have an inversion. And you get this. The entire process start from an achiral starting material. All your molecules you add to it are achiral. You end up with a chiral product. So again, it's racemic. And even though the first step you add the Br and the OH anti to each other, the second step has to go through an anti-coplanar relationship between the oxygen and the bromine, and so it ends up switching the stereochemistry on one. So you invert a stereocenter, and as a net result, you end up with a syn addition. Very similar to the peracid, where cis stays cis, and trans stays trans. Now, I want to talk just a little bit about this step here. Important thing to remember is this oxygen and this bromide must be anti to each other to get the internal SN2 reaction to go. If I give you a halohydrin, like so, before you can, and tell you to treat it with base, like sodium hydride, the hydride will deprotonate that oxygen. Or whatever base that you add. But, important thing to recall, to remember, is this next step, where the oxygen adds the carbon and kicks the leaving group off, is an SN2 step, meaning it has to have a backside attack. So that oxygen has to attack from behind the carbon-bromide bond. So you need to redraw this molecule like so, in order for you to actually do the elimination, where the nucleophile and the leaving group are anti-coplanar to each other. So we rotate this BR 180 degrees. So that makes this, when we rotate this 180 degrees, get that. We can double check this. 1, 2, 3. That's an R stereocenter. 1, 2, 3. Actually, excuse me. That's actually is an S stereocenter. And this right here is an S stereocenter. I can attack, kick the bromide off, and as a result, you get this molecule. Now this is racemic, then this is racemic. If I give you one where this is optically active, because this is chiral, this becomes optically active as well.